Yo, what's up? I'm back, and I'm gonna be doing this problem that I found at Everest. And I actually seen this problem before, so it's pretty famous. So yeah, let's just do it. Yeah, so three connected blocks are pulled to the right on a frictionless table by a force magnitude of T3 equals 65 newtons. If M1 equals to 12, M2 equals 24, and M3 equals 31, calculate the following quantities. So the first one is acceleration, second one is tension, and the third one is the second tension. So yeah. So in order to find the acceleration of the blocks, use a cool trick. Basically, we can say instead of this being three separate blocks, we just make one big block that hold on with a force T3. And we do this so that we can ignore these little forces, like these little T1s and T2s. It gets pretty annoying because you're gonna have to draw a free body diagram for each one of them. So instead we can just treat it as just one whole thing. And this goes for other things too. Like if I had a pulley problem like this, oh shoot, like yeah. So this will happen in like when we get to if I have a pulley problem, instead of at this as like a pulley, I can literally make this one big and this is just this is that. It equals to that. So yeah. It's like the box method type stuff. We'll definitely cover those a lot of Morn problems. Studying for FELS MA, I did so many like blue Morn problems. I'll probably cover this like because every problem honestly. So yeah, blue Morn. So yeah, if you want to see those more, then yeah, I'll cover it. So we so in all we just treat it as one big system, one big like block, and this block has a mass of 12 plus 24 plus 31. So I don't know what that is. 12 plus 24 plus 31. So you get 67. And basically, according to the free body diagram, this block is getting hit with this. It is accelerating. It says find the blocks. It can't just be like find the acceleration and be like, oh, it's zero. I mean, it's accelerating. We all know it's accelerating. It's just pretty intuitive. Yeah, we're gonna use Field's MA. The only force on this object is T3, right? It's sum of the forces MA. If there was like a friction force, then it'd be T3 is friction force. But there's only T3. There's only one force, and that's T3. So the sum of the forces is T3, um, equals to MA and 67, and this is going to be 65, the tension force. So we get A equals 65 over 67, and we have this as our um acceleration 0.999 approximately. Let's just say that. So yeah, let's see. This is acceleration. Now we need to find tension one and tension two. So tension one is actually easier to find here because if you think about it, for M2, tension force, and you have this, so it's pretty annoying. But this is for mass one, right? You have tension pulling this, tension pulling that way. But for mass one, you literally only have so it's a lot easier to do, and we can start off with it because then once we find tension one, we can plug it into here and find tension two. So what is tension one? So T to MA 12 times the acceleration, which is 0.9. By the way, yes, the acceleration is all the same. Why is it all the same? Connected by like the strings, like they're all the same. It's like if you had like a train, right? You know how like trains are like connected by like the little like hooks or something like that. Like this is cargo and it's like the second cargo thing, and it's like connected hooks. They have to have the same acceleration because if this was going faster than this one would just like slip off. So yeah, they're all connected. You can try to think about it like that. That they're all connected, they have the same acceleration. If they're connected, they have the same acceleration. It also applies to pulleys too. Like these two, they right, these are connected by the string. right? Because think about it, if you just remove this, like, this string is going over. So if you get rid of this, you literally just have these two boxes, and they're connected by the string. Similar to this is connected by the string, and these two have the same acceleration. So let's say this one had bigger mass. This would go up, this would go down. They would have the same magnitude of acceleration, but it'd be different directions. Here we know it's the same because intuition. So yeah, this is gonna be tension one. So yeah, tension one times 12, all the way to 6 is the first 0.6, I think, for the some points. Pretty sure. Yeah. Oh, 6.4. Bad. I low-key might be brain rot. I'm actually trying not to this feels so weird to say because it's definitely like socially outlawed now. But like I don't want to say like 6.7 anymore. I just want to say 67. But like it's the rot, man. It's pretty bad. So yeah, this is the first one. For the second one, we have what is the sum of the forces? Remember the sum, right? We're seeing vectors. How do we add vectors? Tip to tail, I guess. Yeah, it would work here too. We're adding vectors. Forces are vectors. So how do we add this? We this T1 tip to the tail of this 2 tip to the tail of the T1 vector, and we have this vector, right? Of T1. So we put this tip to this tail, and the resulting vector is going to be this one. This is the resulting vector, T2, T1. That's how you can think about it. Because remember, they're in opposite directions, so they have to be subtraction. So yeah, MA, right? And we already know that T1 is 11.64. So yeah, 24 times the acceleration, remember, it's the same. 7 plus 0.4, 5 here. Oh wait, we could just use this expression. No, 11.64 plus 24, 0.94. And we get, yeah, 34.92. So yeah, it's easier. Yeah, yeah, so thanks for watching, and I'll see you on the next video. And this is T2.